I can even re-express. This is just a note that in some year, some academic year, earlier year, this very number came, and it can also be expressed this way. But we shall use it the way it appears. If I choose to pick 1 out of k, and apply indices, I can express this 1 out of k is out. This expression and this have the same base but different powers. And when we bring this up, I will clearly show all the working. We get x to the power k, which is this upper term, times x n to the power k minus 1. But if it rises, it is negated. If it rises, it is negated. That means the k will become negative and the 1 will become positive. Plus a times, I can leave this down here as that. I am using a concept of separating the numbers, i.e. if I have a plus b over c, I am separating the numbers to show that it can be a over c plus b over c. Now, if I proceed, this very expression I said could be re-expressed as 1 out of k into, if I use indices directly, I'll have the base, which is x to the n, k minus k plus 1. So it means that the k will cancel, and I will simply have xn plus a over xn to the k minus 1. These two expressions are exactly the same. So that very number 5, part A, could be set, and instead of this, I ask students to show that the formula will actually be this. Now for part B, the number that we are supposed to find out is now 64. And the error, we are told that the error is less than. If the number is 64, it implies that our A is 64. If the error is less than 0.00, it should have been, allow me correct this, it should have been that. Otherwise, the number of iterations you tried out may not actually converge at the time expected. So the tolerance should have been that figure, 0.001. That implies that they are telling us to give our answer to 4 decimal places. That's what it implies. And therefore, it also implies, that is interpreted to mean that we should work with 5 decimal places. It implies that we should work with 5 decimal places. Note that if our TL is 0.0001, which are 4 DPs, it implies, it is important for you to note, it implies that we work with 5 DPs so that we round off our answer at the very end. Our A is 64, our tolerance is that, and we can choose to take our first approximation as 2. If we let our x naught be 2, we shall work steadily using our formula to find the first approximation here. We substitute in here. Our x naught is 2, so we have 2 to the power k. Now, k is the 5th root, so it means that we have 2 to the power 5, that is 2 xn to the power k. It will be our xn. I am using this expression here. And our K, our A is 64, our K is 5. So if I take in 5 minus 1, I will have a 4. I'll have a 4 here. Let me substitute it like that. 2 to the power 5 into 5 minus 1 plus 64 over K, which is 5, times 2, which is the x naught, to the power 5 minus 1. For the next substitutions, I'll be putting this as 4 permanently. So our x1 will actually become 4 times 32 plus 64 all over 5 times 16, which is 80. So if you compute with your calculators, you will have a value I pre-computed already, but for this one we can work through together. 32 times 4 plus 64 all divided by 16 by 5 is 80. Will give you a value of 2.4. After getting 2.4, you are expected to get the tolerance. x1 minus x naught modulus will give us 2.4 minus 2, which will give us 0.4. And we say that 0.4 is still greater than 0.001. This implies that we need to take a second iteration to look for x2. To find x2, we shall feed in our x1 as that. And my dear students, I already emphasized that I am going to be putting this straight away as 4, as you've seen, and this as 4. So I'll have 2.4 to the power 5 times 4 plus 64 over my K, which is 5, times 2.4 to the power 4. When you compute this, the value of x2 you will get, when you compute that, the value of x2 you will get will be, I told you we are working with 5 decimal places. Here we had 2.4 straight away, but now we have 2.308. The other value, 2.30581. We again proceed and look for the tolerance. x2 minus x1 modulus will give us our 2.30581 minus 2.4. The value we get here will be 0.09419. 0.09419, which is still greater than this value. That still emphasizes that we need to take another iteration to look for x3. So we shall get x3 as we feed in this value here. So we have 4 times 2.30581 raised to the power 5 plus 64 everything over 5 times 2.30581. This is raised to the power 4. When we compute using your calculator once again, when you compute this, you will get your x3 as 2.29746. We look for the tolerance by subtraction. If you subtract this 2.29746 minus 2.30581, it gives us a value which is still greater. This value is 0.00835, still greater than our 0.0001. We try the last time until when our tolerance is less than this value. So we feed in now this value as our x. So we have 4 into 2.29746 to the power 5 plus 64, and divide all this by 5 times 2.9746 to the power 4. This gives a value now of x, the power 4, as 2.29740. If we check the difference here, which I will complete right over here, we check the difference, that is x4 minus x3 modulus, we shall get 2.2940 minus 2.29746. Using your calculators, this is going to give us a value. You notice that the first 4 values, 247. This should be 47. Otherwise, it will have a problem there. 4747. So if we take the difference, this is 47. These first values are the same, 294. So we get 0.00076, which is now less. There are 4 zeros. It is supposed to be now less. 29. There is a 74 here. 29740. So it gives us this value. And 0.00006 is less than 0.000. There were 3 zeros, 1. Now that we have got a TO error that is less than the error that was given, we confirm, therefore, that the fifth root of 64, which you can write as this, the power 1 out of 5, is actually 0.297. We need our answer at 4 dPs, so we shall end with a 2974 to 4 dPs. We take that as our final answer for this number. I think those that have been following from the start, this is the third lesson. It is the third lesson under Newton Raphson, and I have said it is the final lesson. It is important that students now should have the capacity to actually correctly do a number under here. You can verify. I want to emphasize that if you directly used your calculator to find the fifth root of 64 directly, it should be able to agree with the answer we have got to the same number or the same degree of accuracy. You must get exactly this. But we have used a formula that we are calling the Newton-Raphson method formula. Part C is a number that I am going to interpret as we proceed. They say repeat part A for the cube root of a number n. The number in question is n, and they want the cube root. This implies that if we let x be the function, it implies that the function that we are going to use, if we let x be the variable, it means that x is actually equal to n to the power 1/3. That's what it implies when they say to find the cube root. Now, if we cube both sides, we shall get that x cubed is actually equal to n, implying that x cubed minus n is equal to 0. And therefore, the function we are going to use, f of x, is going to be x cubed minus n. We need to differentiate this function, which will give us 3x squared. And we need to express this function in terms of x to the approximation of n. And this will give us xn cubed minus n. And therefore, the first derivative to the xn will be 3xn squared. After getting these values, as you are aware, the next part is stating the formula, because they want us to derive the expression and use that expression to find the cube root of 8. And use that expression to find the cube root of 8. So if we use the expression that the general expression is xn plus 1 is equal to xn minus f of xn over the first derivative of f of xn. We simply now substitute in here. We have a first derivative, we have our function. So our xn plus 1 becomes xn minus, our function is xn cubed minus n, but this must be bracketed, over 3xn squared. We do the mathematics of putting it under a common LCM, and our common LCM is 3xn squared. If we divide 3xn squared by 1, we shall get here 3xn cubed. 3xn squared times xn minus, this will just stay the same, but the integers knowledge will come into play, where the n will become a positive. So we have our xn plus 1 being equal to that. If we simplify 3x minus 2xn, we shall get finally the expression which I'll write here as 2xn cubed plus n all over 3xn squared as the expected formula. As the expected formula, that is the Newton-Raphson formula. They are telling us, determine the cube root of 8. To determine implies that the number they are talking about here is 8. And I told you sometimes they will not give you the first approximation. Whenever they don't give you the first approximation, you must be able to work with the values that you ought to use to actually find the cube root. But whenever you reach here, it is important that you define n by writing out the values of n as varying factors. Now, if they tell us find the cube root of 8, we are going to consider, we all know the value of the cube root of 8. Those who do not know, then they should be able to note that if they say find the cube root of 8, they are telling us to find 8 to the power third. So we shall take an approximation. If we take, if we choose x naught to be equal to 2, assuming that we take x naught as 2, since they do not specify the number of decimal places, then it means our next approximation will be 2 times x naught, which is 2 cubed plus n. Our n is 8 over 3 times 2 squared. So our x1 will become 2 times 8 is 16 plus 8 will be 24. And 24 will be divided by 3 times 4, which is 12. And we shall get 2.0. If we look for the tolerance, we shall get 2 minus 2, which will give us 0. And if there is, if this is to the one decimal place, it means that the error is 0.05 there, 0.05. So 0 is less than 0.05, and this implies that we can say that the cube root of 8 is actually 2.0 straight away. But if someone took the first approximation as 1 or 1.5, then you would have very many iterations before it converges to the answer. You would have very many iterations before it converges to the answer. There are many questions they can ask you. The other one was the fifth root, the kth root. So they can say the square root, the cube root. Now this was the cube root. If they say the square root, it means we shall assume that the variable is equal to the number they have told you squared, or to the square root, to the power half. And therefore, where we have x cubed, we would be having x squared, and would go on using the same arrangement to get the number in question. As I emphasized, or as I have been emphasizing over time, these examples that we have worked through are all different in their own way from each other, and therefore they give you an advantage or an exposure on various ways of doing these numbers. We look at number 6. We look at number 6. We look at number 6. And I want to assume that the followers have finished capturing all this work. So allow me clear off this work so that we can work through number 6. Just like one of the numbers we did in our previous lesson, and all the other numbers, I've told you that this topic requires students to have good knowledge of differentiation of given expressions. It requires students to have good knowledge of differentiation. Number 6, so our example number 6 is talking about deriving a formula for the natural logarithm of a reciprocal of a number n. We already know when we talk about the natural logarithm, like we saw earlier, means log to the base e, which we write, if it is x, which we write as ln of x. We already know this. So if they want us to find the expression of a natural number, this x here has been given to us as n, but they are saying the reciprocal. So we are interested in finding the ln of 1 over capital N. In other words, the variable that we are going to talk about, x, is going to be let be equal to 1, the ln of 1 over the reciprocal. This could also be written as the log to the e of 1 out of n, if you want to understand that. So I want proceed and say that since we already know that using indices 1 over a number can be written as that number to the power negative, we can say it is the same as ln of n to the negative 1. This is still acceptable. That our x is equal to this can be written as that. And as you are aware, I will again put a recall under logarithm rules that log a to the power c of b is the same as c log ab. So if I apply that same reasoning, I can say that x is actually equal to negative 1, the natural log of n. Negative 1, the natural log of n, if you follow that rule. And therefore, I could choose to go ahead and say that if I choose to divide by the negative throughout, such that I eventually get another value, I could choose to divide by the negative and say if I divided by the negative, divide by negative, I would get that my ln of n, because this negative will cancel, will actually be equal to minus x. But I will go back there. I will say, but my ln of n can be written as the natural log to the e of n being equal to negative x. And I will say that since log a to the b being equal to c implies that b to the c is equal to a, again there is another rule I'm quoting here. Since this rule dictates that, I can now write this as n being equal to e to the negative x. N being equal to e to the negative x. These steps are very important. Of course, under your working as candidates, don't expect these arrows. Don't take them as standard, but I'm using them to keep on emphasizing the different interpretations that I expected. And therefore, I can say that my function, I can therefore say at this stage, my function f of x that we are going to work with can be n, or can be e to the power x negative minus n. E to the power negative x minus n. And remember, we need to differentiate this. Earlier, in one of our lessons again here, I differentiated. So here I will simply quote, I think you can remember, that e to the negative x, if we differentiate e to the positive x, it stays e to the positive x. But since there is a negative, we differentiate the power, which will give us negative 1 times e to the negative x. So when we differentiate that, we get that negative. The 1 times any number remains 1. So this would be negative e to the negative x. D by dx of e to the negative x is equal to negative e to the negative x, which is here. I will now bring in the first approximation. I will now use the formula and baptize my x with n. Following this, therefore, I can proceed and say that my xn plus 1 is going to be equal to my xn minus the function is e to the negative x minus n, and the derivative is minus e to the minus x. But I told you those brackets are very key. The rest will be now mathematical. So our xn plus 1 will become, if we multiply here, we'll have xn negative, because this is negative, e negative x. Those who are following, do not say, where has this negative disappeared? I've written it first. If I open brackets, that e would stay negative, the first one, but the n would become positive. And the whole of this expression is now under a common denominator. Remember, wherever we have our x, it has an n subscript. If you forget it, you will now be wrong. We can choose to leave it there. We can choose to leave it there. We can choose to factor out our e to the negative xn. If we factor out, we can take e, the negative xn, as common. That means we'll be able to stay. If this is pulled out, it is shared here and shared here. We shall stay with, we can make this xn plus 1. We can make this negative. This negative, when it enters up here, everything will be positive except this. So we can say it is, this negative would die with this, and make that positive. So we can say we have xn plus 1 minus n over e xn negative. That can work now as our final expression. As our final expression for the Newton-Raphson formula for finding the reciprocal, for finding the natural logarithm of the reciprocal of the number n. This becomes our Newton-Raphson method formula, where our n is equal to 0, 1, 2, 3, and so on, up to infinity. That is our expression, but they are telling us that we should find the ln of 2 out of 3. Find the ln of 2 out of 3 to 3 decimal places. Find the ln of 2 out of 3 to 3 decimal places. But they are giving us an approximation which I will be sharing with you. So to find ln of 2 out of 3, remember that the question says find the natural logarithm of the reciprocal of the number. So it implies that if it's already fitted in here, it is already reciprocal. So the number is expected to be 3 out of 2. The number n is expected to be the reverse of what you see there. And our first approximation, which should have been given, we are going to let our x naught be negative 0.35. Our x naught is going to be negative 0.35. When you are given the first approximation, you automatically generate the TOL if it is not given. I told you this becomes 0, that becomes 0, that becomes 0, and this is 5. That becomes the error in that number. The error in the number given is 0.00 and 0.00. We should have one more 0 here. They give a tolerance. These should have been given in that question. So we are expected to start by finding x1. Find x1. To find x1, we are using this formula, and we are feeding in x naught, where n is 0, as negative 0.35. So we have e to the negative 0.35, which will now become positive. Negative will become positive, into the x naught, which is negative 0.35 plus 1, minus the n. I told you the n is 3 out of 2, which I can write as 1.5, all over the e to the negative, which will now become positive again because of negative. When you use your calculators, which I will expect you to use your calculators to compute that value. Use your calculators to compute that value. Use your calculators to compute that value. You should be able to get the first answer as negative 0.4070. Because they are saying 3 decimal places, we work with 4 decimal places. That is our first value there. We check for the convergence, x1 minus x0. We have our negative 0.4070. We take away 0.35. We take the modulus. Of course, this is going to become plus. So if you get to this modulus, it will give you a value. You are checking, is it converging yet? It will give you a value of 0.0570, which is still greater. That is still greater than our tolerance value of that. That means that we need to take it one more step. And I will have to clear this side to create space. Our learners, if there is anything you need to capture, I will request you to capture, because I will shortly be clearing space here. I need to find x2, and now my x1 is going to be what I will feed in our formula. So I'll have my e to the negative. This negative will die out, so I'll have 0.4070 all into my negative 0.4070 plus 1 minus our n. Our n is constant, all divided by e to 0.4070. Again, if you compute that, it will give us the value of x2. Check for the tolerance or the error range, and if it is still greater than the TOL, you need another iteration to do. When you compute that, the value of x2 you get will be negative 0.4055. I told you we are using 4 dPs because the answer requires a degree of accuracy of 3 dPs. Check for the tolerance. x2 minus x1 will give us negative 0.4055. This will be plus 0.4070 modulus. And what do we get? When you compute this, you get a value of 0.0015. This is still greater than 0.0005. So it means we need to look for x3. We feed in this, and we have our e to the 0.4055 into our 0.4055 plus 1 minus 1.5 all over e, the 0.4070. 0.55. The negatives die out. Our x3, you can still compute. Not forget that this is the negative. When you compute, that will give you a value of x3 as negative 0.4055. Negative 0.400055. If we look for the difference, this time, the difference is going to give us x3 minus, which is plus 0.4055, and this time round gives us 0, which is less than the 0.0005, implying that we have reached the convergence, and therefore it implies that the mean of 2 out of 3, which they told us to find, is actually going to be this answer, but to 3 dPs, it's going to be negative 0.406 to 3 decimal places. To the degree of accuracy required by the question, we will be able to get our answer as that. We will be able to get our answer as that one. Our answer to that number will be that. Our answer to that number will be that. As you finalize that, I wish to put one number here that is a bit unique. Probably I can mention something about it before this lesson ends to get you started. Otherwise, I expect that you should now be experts under this area. This one requires plotting. Yes, that number is going to close our lesson today. And I can only be privileged to take you through the first part. The second part I am confidently sure you can handle. I will be able to take you through the first part, and I want to emphasize that the second part, I am sure you are able to handle it. The second part, I am sure you are able to handle it. You are free to take a picture of this number so that it allows me time to interpret the first part, which is very important. You are given an equation. I'll call it a function, x e to the negative x minus 2x plus 5. And they are saying, okay, this function is equal to 0 if I remove this. By plotting suitable graphs, this function will be broken, or this expression will be broken into two expressions. We shall break it into two equations to form, I'll call them y1. Let y1 be equal to x e to the negative x, and y2 be equal to 2x plus 5. Now, it is 2x plus 5 because if we equated the 2, this will go the other side. Therefore, if this goes the other side, this will be a negative. So to plot them on one graph, we will have to find their coordinates for both. Very fast, if I choose to use values ranging from 0 up to 4, for the first case, you feed them in and get their corresponding y values here. If we put in 0, this will be 0. If we put in 1, we shall get e to the negative 1, and that is 1 over e. Those who know what e is, you get 0.38. Here you'll get 0.27, and here you'll get 0.15 upon computation, and you get 0.07. For this one, you can choose to use 1, 2, 0, and 0 there. You are all aware that if you are plotting a line, if you put x as 0, y is negative 5. If we put y as 0, x is 2.5. And if we put 1 as x, we have negative 3. 2 as x, we have negative 1. So finally, they are saying by plotting on a suitable graph. I want to emphasize that if I chose this to represent my graph, I'll start with 0, negative 5 here. If this is negative 5, that will be that, and 2.5. If my 2.5 is here, I can ably join these 2 points to form a line, which I will label y is to x minus 5. Now, if I sketch the other one quickly, 0, I have 1, 2, 3, 4. If I take the values there as 0.1, 0.2, 0.3, 0.4, quickly, 0, 0 is here, 2.27, maybe I assume it is there, 0.15, somewhere there, that is 3, somewhere there. 4, 0.07 would be somewhere there. So if you join these, you obtain some kind of curve. Now, where they meet, they are supposed to be meeting somewhere slightly before this point. Where they meet somewhere, not necessarily at 3, we'll confirm that there is a root here. The fact that you need to use here is that since this is on the x-axis, the positive x-axis, then this is a positive root. It's a positive root, and it is real. It is real, meaning it is not imaginary, and therefore it can be read off. This root can be read off from your graph if you have done it accurately, and this root gives you the first approximation when you are looking for the answer there. This root that you read off here will give you the first approximation when you are looking for that answer. I have looked at all the parts that one would require to be able to do any number on Raphson method. I will, as I close, I will ask you to try. There are very many numbers in the question bank, but among others, I gave you some the other time, but you can try these ones out. You can try these ones out, and they should be able to set you rolling. They should be able to set you rolling. Try these numbers out, and you will not regret. I want to wish you the best. When we meet next Monday, we shall definitely be looking at a new topic. God bless you. Teacher Kakuru Gachali Mabaga.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts and sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne bw'osomeseza omwana wo mu masomero ga Giant Schools omuli kampasi y'Ebombo Kalule n'ey'Ekabalagala toba na bweraliikirivu bwonna olw'omusingi okutambuzibwa ebyenjigiriza n'ensoma y'abayizi ey'omulembe. Mu masomero gaffe gano gonna tusomesa arts and sciences okuviira ddala ku siniya esooka okutuuka ku siniya ey'omukaaga nga tusomesa abaana okuviira ddala ku mutendero gwa kindergarten okutuuka ku kibiina eky'omusanvu. Tulina abasomesa abakugu mu kubangula abaana n'okubateekateeka. Ebibiina abaana mwe basomera eby'omulembe omuli buli kimu ekikwata ku ebyo bye basoma, ebisuula ebyazimbibwa obulungi, ebigazi ate nga biyonjo. Okumanya ebisingawo tukubire ku nnamba z'essimu ezowammanga.
Baby Junior Jelly owulira omukwano gwa maama n'okufaayo kwa maama. Baby Junior Jelly owulira engalo za